Hello, just going to take you through the answers to 26.5 radioactive decay if you need a little bit of help. So if you check at the top of the questions, this number here is Avogadro's number. It's 6.02 times 10 to the 23. It tells you the number of atoms in a mole of a substance, and you need it in question 4. It also tells you here 1 mega electron volt is 1.6 times 10 to the minus 13 joules, which is a handy shortcut later on. So in figure 1, in question 1, it asks you to look at figure 5, which is here. I've added some lines. We'll go through that in a minute. It shows you how the mass of a certain radioactive isotope decreases with time, and you need to use a graph to work it out. So first thing to do is work out the half-life of the isotope. So the initial mass is 48 milligrams. If you check here, milligrams on the unit, 48 here. Okay. Half-life of that will be when it is 24 milligrams. So then you use the graph, go to 24, which is here, across and down, and then you get the times 40 seconds. Second part wants you to work out the mass of the isotope after 120 seconds. So figure out how many times 40 fits into 120. That's 3. So it's gone through 3 half-lives, okay? So the mass remaining will be 16. Hang on, let me just check that. Sorry, I was rushing making this and I realised I did the last bit wrong. So you don't divide it by 3 at all. You do use that little formula I talked you through. So the half-life, so the fraction you're decreasing by is 0.5. You've got 3 half-lives, you put 0.5 to the power 3 and then times it by your original number, which is 48. So the answer is 6 milligrams, okay? You completely ignore what I did before. I was having a brain freeze. Okay, question 2. You've got a freshly prepared sample of radioactive isotope X and it contains 1.8 times 10 to the 15 atoms of that isotope. And the half-life is 8 hours. Calculate the number of atoms of the isotope remaining after 24 hours. So my N0, my initial number is 1.8 times 10 to the 15. T half-life is 8 hours. So after one half-life, which is the first one, okay, the number will have halved, so I just halved it, so it's 9 times 10 to the 14. After 24 hours, 8 fits into 24 3 times, so then you use that little handy calculations. You've got 0.5 to the power 3, which is the number of half-lives, times your original number of atoms, and it gives you 2.25 times 10 to the 14. Technically 2.3 times 10 to the 14 to 2 significant figures. For part B, it tells you the number of atoms that would have decayed. So you're looking for that other fraction. So so these formulas tell you how many are remaining. So then the original number take away these numbers will give you how many have decayed. So in the half-life, half of them have decayed. So that means half have remained and half have decayed. For the other one, you just need to calculate. If you do what you initially had here, take away what you've got left over, which is here, you get what's left, which is 1.58 times 10 to the 15, which is 1.6 times 10 to the 15 to 2 significant figures. And then the energy transfer from the sample in 24 hours if the isotope emits alpha particles. So the number you're looking for is how many have decayed. So, because that's how many alphas you've got. So this is the number you've got. This is how many alphas, and each one has got 5 mega electron volts of energy. So if you're going to start from scratch, you would just do this number here, number that have decayed, times 5 times 10 to the 6, which is mega, times 1.6 times 10 to the minus 19, which is electron volts. You get 1264, which is equal to 1,300 joules to 2 significant figures. You can use the little shortcut, which is start, which tells you how many mega electron volts are in 1 joule, in which case you do the number at the start times 5 times this number. Question 3, you've got radioactive iodine, 13153. It has a half-life of 8 days, and it has an initial activity of 38,000 becquerels. Calculate the activity of this sample 8 days later. So again, it follows the half-life rule. So T half is 8 days, and there's your initial activity. So 8 days is 1 half-life, so the activity would have halved. So I've just halved it there. So you get 19 times 10 to the 3 becquerels. 32 days, you need to find out how many half-lives that is. So 32 divided by 8 is 4 half-lives. So then you can use your nifty little calculation here to figure out the activity then. 0.5 to the power 4, because it's 4 half-lives. And then times the original activity. So 38 times 10 to the 3, you get 2375, which is 2,400 becquerels. Last question. Last question will be difficult if you're not very good at chemistry. If you're good at chemistry, it should be fairly easy. It just relies on you knowing how to figure out how many moles you have. But I can talk you through it. So it tells you in the question you've got 13755CS is a radioactive isotope of cesium. It has a half-life of 35 years. A sample of this isotope has a mass of 1 times 10 to the minus 3 kilograms, so basically a gram. And it says calculate the number of atoms in 1 times 10 to the minus 3 kilograms of this isotope. Now, in order to do this, you need to know how many moles are in the atom. And it tells you, at the start, it told you Avogadro's number. Avogadro's number is how many atoms are in a mole. So first thing to do, if you have 137 grams of this cesium, so I'm looking at the top number here, the mass number. If you have 137 grams of that, that is 1 mole, and it will have Avogadro's number of particles. So the number of moles that you have in total will be the mass that you have, okay, here, divided by the molar mass, which is 137 grams. So you've got 1 times 10 to the minus 3 kilograms divided by 0.137 kilograms. So I've just converted this grams into kilograms. That gives me 7.3 times 10 to the minus 3 moles. So the number of molecules you're going to have, N, will be equal to the number of moles, which you've figured out here, times Avogadro's number. So if this number here was 1, you would have Avogadro's number of molecules. But it's not, we've got less than a mole. So we're going to do 7.3 times 10 to the minus 3 times 6.02 times 10 to the 23. And that gives me 4.4 times 10 to the 21 atoms. So that's how many I initially have. If you struggle with that, understanding that because you don't do chemistry or you aren't very good at it, we cover it again later, and I'll make sure I cover it again when you come back to school, okay? Anyway, it says calculate the number of atoms remaining of the isotope remaining in the sample after 70 years. So 70 years is 2 half-lives because a half-life is 35 years. So using your nifty little calculation, 0.5 to the power 2 because it's 2 half-lives times the original number of atoms, 4.4 times 10 to the 21. So you get 1.1 times 10 to the 21 atoms left. Okay, hope that helps. See you soon.